Greetings, everybody. Learning is a hobby here. I want to go over the exercise set in chapter 30 for Spivak's calculus book. So that's what I'll do in this video. And once we get through this, we'll be done not only with chapter 30, but we'll be done with the epilogue for Spivak. So we'll be able to go back to part and begin on part 3 of the book, which is on derivatives and integrals. So that's exciting. So let's get to it. This is a relatively short exercise set. There's only 5 problems, and none of the problems are particularly difficult, so it shouldn't take us too long to get through these. So we'll do that, and then, like I said, we can. Well, I'll start by going back to part 3 of the book. So let's begin here with question number 1. So let F be an isomorphism from the field F1 to the field F2. There's 2 parts to this question. Part A says show that f of 0 is 0 and f of 1 is 1. So we'll start by showing that f of 0 equals 0. Okay, f of 0 is equal to f of 0 plus 0, which is f of 0 plus f of 0, because f is an isomorphism and therefore a homomorphism. And that implies that 0 equals f of 0 plus the negative of f of 0. That's a property of fields, right? Which is equal to f of 0 plus f of 0 plus minus f of 0. Um, oh, that's from up here. Sorry, adding f of minus 0 to both sides. Okay, which is equal to 0, which implies 0 equals f of 0 plus f of 0 plus minus f of 0 by associativity, which is equal to f of 0 plus 0, which is f of 0. Again, that's a property of fields. Okay, so 0 equals f of 0. Then second property, f of 1 is equal to f of 1 times 1, which is f of 1 times f of 1. Furthermore, f of 1 is not 0 since f of 0 equals 0 and f is 1 to 1 because it's an isomorphism. So f of 1 inverse exists. Then 1 equals f of 1 inverse times f of 1, which equals f of 1 inverse times f of 1 times f of 1, which is equal to f of 1 inverse times f of 1 in parentheses times f of 1. Again, that's the associative law. Remember, we're working in a field. That implies that 1 equals 1 times f of 1, which is f of 1, so 1 equals f of 1. And that's part, was that part A? Yeah, part A. And then part B says this. I shouldn't have, so this should have been a part B, not 2. Let me just fix this in the notes. Okay, so part B says show that f of minus A equals minus f of A, and f of A inverse equals f of A inverse for A not 0. So let's do the first part. Uh, by the previous part A, 0 we know is equal to f of 0 equals f of A plus minus A, which is equal to f of A time plus f of minus A, which implies that negative f of A equals negative f of A plus 0, which is negative f of A plus f of A plus f of minus A, which implies negative f of A equals negative f of A plus f of A in parentheses plus f of minus A, which is 0 plus f of minus A equals f of minus A. Therefore, minus f of A equals f of minus A. Okay, and then second property, let A not 0, then 1 equals f of 1 equals f of A times A inverse, which is equal to f of A times f of A inverse. Again, that's just a homomorphism property. Implies f of A inverse, which is equal to f of A inverse times 1. That's a field property, which is equal to f of A inverse times, in parentheses, f of A times f of A inverse equals, again, associativity here, f of A inverse times f of A times f of A inverse implies f of A inverse equals 1 times f of A inverse, which is f of A inverse. Again, field property. So that shows what we wanted. All right, that's question number 1. Like I said, pretty straightforward. Question number 2. Uh, Spivak has a little bit of an explanation here before we start on this one. Here's an opportunity to convince yourself that any significant property of a field is shared by any field isomorphic to it. The point of this problem is to write out very formal proofs until you are certain that all statements of this sort are obvious. The field F1 and F2 will be 2 fields which are isomorphic. For simplicity, we will denote operations in both by just the usual plus and multiply sign. So there's a bunch of parts that he wants us to do here. So part A says, if the equation x squared plus 1 equals 0 has a solution in the field F1, then it also has a solution in the field F2. All right, so let's do that here. So let F from F1 to F2 be an isomorphism, and that there is X in F such that x squared plus 1 equals 0 in F1. Then 0 equals f of 0 equals f of x squared plus 1, which is equal to f of x squared plus f of 1, which is equal to f of x all squared plus 1. That's the homomorphism property again. So um, that shows that there's a solution in the field F2 to that equation, right? Proposition in part B says this: if every polynomial equation x to the n plus a to the n minus 1 times x to the n minus 1 plus dot 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 plus a0 equals 0 with all of the coefficients, a sub j in the field f1 has root in f1, then every polynomial equation xn plus bn minus 1 yada 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 equals 0 with b0 to bn minus 1 in f2 has a root in f2. So this is very similar to what we just did. Let b0 through bn minus 1 be elements of the field f2. Then there are a0 through an minus 1 such that b0 equals f of a0, et cetera, down to bn minus 1 equal af and equal to f of an minus 1 for some, a0 through an minus 1. That's because f is an isomorphism, so it's on 2, right? Then a0 plus dot 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 up to an minus 1 times x to the n minus 1 plus x to the n equals 0 for some x in f1. Then again, 0 equals f of 0 equals f of that polynomial, which is equal to f of a0, use of the homomorphism property equals f of a0 plus dot 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 up to f of a n minus 1 times f of x to the n minus 1 plus f of x to the n, which is equal to b0 plus dot 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 to bn minus 1 times f of x to the n minus 1 plus f of x to the n. And that shows that if x is a solution to the equation with the a's, then f of x is a solution to the equation with the b's. All right. Proposition C says if 1 plus 1 plus dot 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 up to 1 summed m times equals 0 in f1, then the same is true in f2. Again, this is very straightforward. 0 equals f of 0 equals f of 1 plus dot 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 up to, m times, right? Adding 1 n times equals by the homomorphism property f of 1 plus dot 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 plus f of 1 m times, which is equal to the multiplicative identity in the field f2, 1 plus 1 dot 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 m times, and clearly that's equal to 0. So that works. And then part D, if F1, F2 are ordered fields and the isomorphism F satisfies f of x less than f of y for x less than y, and f of 1, f of 1, not f of 1, sorry, f sub 1 is complete, then f2 is complete. All right, so here's my proof. Let A be a set of elements of F2 that is bounded above. Then define the set B to be the set of all B in F1 such that f of B is in the set A. Then A is bounded above implies B bounded above, which implies that x equals sup B is an element of F1. Then for any b in the set B, B is less than or equal to x, which implies that f of B is less than or equal to f of x. Assume there's some f of A in the set F2 such that f of B less than f of A less than f of x for all B and B. Then B less than A less than x implies A is an upper bound for B, the set B, but x less than or equal to A, which is a contradiction. Therefore, f of B equals A because f is onto, and since f is onto, oh, sorry, I said that twice. F of B equals f of A since f is onto, and f of x equals sup A. Right? That's all the parts in question 2. Question 3 says, let F be an isomorphism from F1 to F2 and G an isomorphism from F2 to F3. Define the function G composed with F from F1 to F3 by G composed with f of x equals G of f of x. Show that G composed with F is an isomorphism. So you just show the 4 properties. So assume G composed with f of x equals G composed with f of y, then G of f of x equals G of f of y implies f of x equals f of y because G is 1 to 1, and that implies also that x equals y since f is 1 to 1. Right, so G composed with f is 1 to 1. Then we have to show that it's onto. Let Z be an element of F3. Then there is Z prime in F2 such that G of Z prime is Z since G is onto. Also, there is Z double prime in F1 such that Z prime equals F of Z double prime since F is onto. Therefore, Z equals G of Z prime equals G of F of Z double prime, which is the same thing as G composed with F of Z double prime. So G composed with F is onto. All right. Property number 3, the homomorphism property. Let x, y in F1 consider G composed with f of x plus y. That's the same thing as G evaluated at f of x plus y equals G of f of x plus f of y because f is a homomorphism equals G of f of x plus G of f of y because G is a homomorphism. And that's the same thing as G composed with f of x plus G composed with f of y. Also, same thing for multiplication. G composed with f of xy is G of f of xy, which is G of f of x times f of y, again, because G is a homomorphism, which equals G of f of x times G of f of y, because G is a homomorphism, and that's the same element as G composed with f of x times G composed with f of y. Right, so G composed with f is a homomorphism. Those three things tell us that um, the the function G composed with f is an isomorphism. Okay, question number 4, suppose that F is a complete ordered field so that there is an isomorphism F from R to F. Show that there is actually only one isomorphism from R to F. Hence, this is problem 317. He says, now if F and G are two isomorphisms from R to F, consider G inverse composed with F. All right, so let's do that here. Let F from R to be an isomorphism from R to F, and G, same thing, an isomorphism from R to F, and consider G inverse from F to R. Let AB be elements of F, then there are X, Y, and R, such that G of X equals A and G of Y equals B. Then we first thing I did was I showed that G is an isomorphism. So in other words, um, a plus b equals g of x plus g of y equals g of x plus y because g is a homomorphism implies g inverse. And I should say also, obviously g inverse is bijective because g is bijective, right? So the inverse exists, in other words, right? So g inverse of a plus b equals g inverse of g of x plus y, which is x plus y because g inverse cancels with g, which is equal to g inverse of a plus g inverse of b. Similarly, AB equals g of x times g of y equals g of xy because g is an homomorphism, implies g inverse of AB equals g inverse of g of xy equals xy, which is g inverse of a times g inverse of b. Clearly, g inverse is a bijection, therefore g inverse is an isomorphism from f to r. Now consider g inverse of f from r to r. Then by the previous exercise, G inverse of F is an isomorphism and therefore is a ring homomorphism. So by problem 317, and I'll show you what the problem says in a second, but I actually proved 317 way back when. So if you want to see that, go back to my videos for chapter 3 in Spivak's book. Or you can go to my PDF documents for on the Patreon page for my chapter 3 exercise solutions, and you'll see my solution there. This is what the theorem says, just because I don't expect that you would remember that. This is what 317 says. Assume f of x is not always 0, and that f of x plus y equals f of x plus f of y, and f x y equals f of x times f of y for all x, y, and r. Prove that f of x equals x for all x as follows. And there's a bunch of parts that it's kind of a long proof that we went through to prove that that's the case. So if you want, like I said, if you want to see that, go back to my video, go to the Patreon page. Okay, but we're going to use this theorem here. Okay, so since we know that G inverse composed with F is an isomorphism and therefore a ring homomorphism, then problem 317 tells us that G inverse composed with F of X is equal to X for all X and R, which means G inverse composed with F is the identity function on R, which means G inverse equals F inverse, or in other words, F equals G, and that's the proof. Okay, and then last question, number 5, find an isomorphism from C to C other than the identity function. So here's my solution. Let f from C to C be the function where f of z is the conjugate of z, the complex conjugate of z. Okay, then I'm just going to show that that's an isomorphism. So 1, if f of a plus bi equals f of c plus di, Then A minus BI equals C minus DI implies A minus C plus D minus BI equals 0, which implies A equals C and D equals B, or in other words, A plus IB equals C plus ID. Therefore, the function is 1-to-1. It's also onto because if we let A plus IB be an arbitrary complex number, then A plus IB equals A minus IB complement, sorry, not complement, conjugate, which is equal to f of A minus IB, and A minus IB obviously is a complex number, therefore f is onto. And then finally, we just have to show that that f is also a ring homomorphism. So f of z plus w equals the complex conjugate of z plus w. And if you know about complex numbers, complex conjugation distributes over addition and multiplication. So that's the same thing as z complement. So I keep saying complement. Z conjugate plus W conjugate, which is equal to f of z plus f of w, and f of zw equals conjugate, which is conjugate times w conjugate, which is f of z times f of w. Therefore, f is a ring homomorphism. Therefore, f is an isomorphism from C to C that is not the identity on C. Okay, and those are the exercises from the last chapter in the book, chapter 30. So, we're done with the epilogue and our construction of the real numbers, at least for now. We will be doing one more construction of the real numbers, but later on, when we get back to Tau, I'll do his Appendix B after we finish his chapter on series. So that's in the future. But for now, what I'm going to do is I'm going to go back to part 3 of the book, which starts in chapter 9, and we'll finish part 3 and part 4. Part 4 is about series and sequences. So those are the last two parts of the book. So we'll start in part 3 in chapter 9, and part 3 there's a few chapters in it which is all on differentiation and integration, and then once we're done with that, we'll finish up part 4, which is, like I said, all on sequences and series, and then we'll be done with Spivak's book, which, we've been doing this for a long time. I'm looking forward to it, and I think that those two parts should go by a little bit more quickly than the other ones were, because those topics are a little bit finicky. So thanks for watching, guys. Let me know what you think down below. Give me a like and subscribe. And if you want to see the PDFs of all the documents and everything that I go through on the videos, then you can join the Patreon page for $3 a month, and all that stuff is available to you there. So I'll see you guys in the next one.